So today we're doing section 6.5. I can find the average value. We are not doing a warm-up, but that doesn't mean we won't be practicing doing AP practice. We have an AP practice question. It's just a little bit later on in the lesson.
Is this our last lesson?
Tomorrow is our last lesson. But today's lesson is very short, so you will have at least a half hour to start working on your first quiz for the unit. Tomorrow's lesson is also pretty short, so again, tomorrow you should easily be able to finish that first quiz. Friday, what are you taking?
Big quiz.
Big quiz. When's your test?
Wednesday.
1 week from today. Yes, 1 week from today. All right, Keegan, what's your question? Are we skipping 6.4? Yes, and 6.4, what is 6? Oh, if I remember right, 6.4 is a physics section. Let me refresh my memory on what 6.4 is. Yes, so 6.4 is calculating work done, which is great, and if you take Calc 3, which you will next year, then you'll be calculating work like crazy, but it is not an AP topic, and it just we don't want to get into it. So we don't need to add more stuff into your heads than you already need in there, right? Okay, so yeah, so we skip 6.4. So today we do 6.5, which is average value. Tomorrow we do tomorrow we do 7.7. Which is arc length, because we got to teach arc length, and that's where they, With 7.7 trapezoids? Then maybe it is 6. Here, wait. I'm getting all the sections mixed up now. You shouldn't have asked me, because now I got to look it all up. Let's see. 8.1. Tomorrow we're doing 8.1. Which is arc length. All right. Okay. So today we do 6.5. Tomorrow we do 8.1. Then we're done with the unit. Then we review, test. And then we start chapter 9 next Thursday. Yes. And that'll be that. Chapter 7 we skip almost completely except for the trapezoids, because chapter 7... if I remember right, is almost all a physics chapter, which is kind of fun, but not necessary for this class. All right, so, okay. All right, so average value. So, in the past, when you have been asked to find an average, you have been given a list of numbers. And what did you do? You had Teddy Graham. You add them together and divide by how many there are, right? That's what we've always done for an average. However, what if there were infinitely many numbers in the list? What? You divide by infinity and then you're done. Yes. Okay. All right. So the problem with computing the average value of a function over an interval. So this function right here, this blue line, that represents a temperature throughout a day, right? So 0 to 24 hours, some temperature, I don't have any units. Let's assume it's degrees Fahrenheit, and it's a typical Minnesota day, right? Okay. So anyway, so this is your temperature graph from 0 to 24. What if we want the average temperature, right? How do we find it? What do we do, right? So this is where what we're learning today is how to find an average value of a function over an interval. The average value is like right here. It's like right around 4. But that's what we're going to learn today is how to find an average value of a function over some interval. Oh, I would be happy to do a full screen. There you go. All right. So formula. One formula today. Average value. And all it is the integral of the function from a to b divided by b minus a. It's 1 over b minus a times the integral from a to b of the function. Now, there is a reason for this that I will show you visually in a few minutes. But first, we're just going to write this down, and we're going to do a couple problems with it then I will give you a little bit more info behind the scenes on why this formula works. Now, your book uses the notation F sub ab. That is not universal notation. That's just your book's notation. But I'm using it so that it doesn't freak you out like when you see it in your homework and everything. I personally grew up with a notation that I have not seen in years. So this textbook doesn't use it, and the last textbook we used didn't use it. But when I was a kid and we had to find average value, my teacher always wrote Y bar, called it Y bar. And I had professors that called it Y bar. And it was just Y with a bar over the top meant the average of Y. And that's what I grew up with, but I haven't seen it in like 20-some years. So it must have just faded away. So anyway, so now we're using F sub ab. Yes, Keith?
Like for the stats division. Yeah.
Oh, really? Did they use that for stats? Oh, X bar is the mean.
Yeah.
Oh, that makes sense. So Y bar so X bar means an average of X, so Y bar would mean an average of Y. Oh, there we go. Yeah. Okay, so I'm not crazy, right? But I've never seen it used in a calculus book in 20-some years. So anyway, but thank you for confirming that I was not crazy. It's always nice. All right, everyone have this down? Moving right along. So we're gonna jump right in with an example, and I'm not even gonna show you how to set it up or how to do it. You guys are gonna do it. All right, start to finish. So A and B are the endpoints of your interval. So we're going from negative pi thirds to pi thirds. So I will help you just say this is like your A and this is your B. And we're finding the average value of the function cosine x from negative pi thirds to pi thirds. So I want you guys to set it up and then evaluate the integral and clean up the answer. Nice, simple, reduced fraction. Or simple integer. Who knows? Right? Okay, average value of cosine x from negative pi thirds to pi thirds. So our f, it's not today either. Okay, our f sub ab would be 1 over pi thirds minus negative pi thirds times the integral from negative pi thirds to pi thirds of whatever we want the average of. Whatever goes here, this is what we want the average of, right, is the function that goes there. Right? Whatever you want the average of, that becomes your integrand. All right. Okay, so cleaning it up, this is 1 over 2 pi thirds times, what's the antiderivative of cosine? Sine. So we have sine x evaluated from negative pi thirds to pi thirds. All right, so 1 over 2 pi thirds is the same as 3 over 2 pi. Sine of pi thirds, sine of pi thirds. What is that? Root 3 over 2. What's the sign of negative pi thirds? Negative root 3 over 2. Okay, so what we have is 3 over 2 pi. Root 3 over 2 plus root 3 over 2, that's just root 3. So 3 over 2, I can't say it. 3 over 2 pi root 3 would be my final answer. All right. How's that? Did that work okay? Any questions? No? All right. I'm going to back up and I want to show you something a little nifty for a minute, just so you understand. So quiet down please. When I say that this right here, that's what you want the average of. So do you guys remember sometime in the past we learned this thing called an average rate of change, right? Okay. So average rate of change of f. suppose I wanted the average of the rate of change of f, right? Which is what the AROC is. AROC is the average of the rate of change of f from on some interval a to b, right? That would be 1 over b minus a times the integral from a to b of, what's the rate of change of f? F prime. That's what I want the average of, right? All right. What's the antiderivative of f prime? F. Okay. Oh,
No.
it's amazing, right? Math does work.
Incredible.
All right. So, yeah, so if you ever happen to forget your average rate of change formula, you could do the average value formula on the rate of change, right? Okay, yeah. So there you go. All right. Okay, moving on. So there's a little more to the average value formula. There's kind of an extension on it. It's really just a rearrangement, but it has its own, this rearrangement of the average value formula has its own special name. Now, it's a theorem, but you don't have to do all the theorem stuff for it, okay? So, if T of T is the temperature of let's just say the outside temperature at time T, we might wonder if there's a specific time when the actual temperature equals the average temperature. All right? We did this before.
Yeah, that sounds like a thing.
It sounds like, anyone remember what theorem it sounds like? The mean value theorem. So, okay, now the mean value theorem that we learned was, is there a time when the average rate of change equals the instantaneous rate of change, right? Here, we're just talking in general average value equaling the actual value, right? Okay, so anyway, is there a time? Well, for this function, yeah, there's not just one time, there's 2 times when the actual temperature equals the average temperature, right? Okay, but lucky for us, we have this wonderful theorem. Is this always true? Why, yes, it is, and hence we now have the mean value theorem for integrals, right? Okay, so what does the mean value theorem for integrals say? The mean value theorem for integrals says that that there has to be at least one value c in the open interval from a to b where the actual function value equals the average function value. Now, you don't have to know the theorem in fancy theorem-y speak, okay? You just need to understand and be able to apply it. That's really all you have to do. You don't have to state conditions or anything like that. It's never, ever been like a required standard by the College Board of being able to state the conditions for mean value theorem for integrals. However, you do have to be able to use it. And so that's what we're going to do, is just use it a couple of times just so you understand. So first, I want to show you, though, something kind of neat so that you can kind of learn what the mean value, what the average value means graphically. So if you take this right here, this is the average value formula, right? That's what you wrote down on the the second slide. So you wrote f sub ab 1 over b minus a times the integral from a to b of f of x dx, right? If you take, remember this right here, that's area under the curve, right? So that integral gives us area under the curve. If we take this b minus a and move it up here, what we get is area under the curve equals this. Well, this is a number, right? It's some y value. This is a number. It's the width of your region. What does this actually give you? It gives you a width times a height. This is the area of a rectangle. So the average value is the height of a rectangle with the same area as the area under the curve. So the average value is the height of a rectangle. That's your average value. The height of a rectangle where the area of this rectangle is the same as the area under the curve. All right. You can actually kind of see, like you could take this little chunk here and kind of move it in there and kind of make a rectangle out of it, right? So the average value graphically is the height of a rectangle that has the same area as the area under the curve. The College Board one time did a multiple choice problem and where they gave you graphs of, and they looked just like this, like of a function with rectangle kind of a thing. And they asked something about like which one like has a height that would be represented by the average value. And all you had to do was look at the pictures and see which one could you take this chunk, put it in here, and like make the rectangle out of it. It took like 2 seconds, but a lot of students, so most of our students got that really fast and easy. But if they didn't know that, if you didn't understand it graphically, you had to sit there and find the average value by hand because they gave you a function and you did. So you could do it by hand, but it took like several minutes to do, as opposed to just looking at the picture and moving the chunk. So anyway, okay. So kind of fun, average value, height of a rectangle, same area. All right. So we're going to do now a two-part example. So we're going to, again, find an average value of f of x equals 1 plus x squared on the interval from -1 to 2. Then we're going to find c as guaranteed by the mean value theorem for integrals such that f of c equals the average value. What I want you guys to do is just do the first part. So I want you all right now in your groups, take a minute and find the average value of f of x equals 1 plus x squared over the interval from -1 to 2, and then just stop. All right, so take a couple. All right, here we go. So our f sub f equals 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx. We all comfortable with setup? Yeah. Okay. So you get 1/3 times antiderivative x plus 1/3 x cubed from -1 to 2. So you get 1/3 times 2 plus 8/3 minus -1 minus 1/3. All right, so 1/3 times, so 2 plus 1 is 3, and then 8/3 plus 1/3 is 3, so 3 plus 3 is 6, so we end up with, okay. It's all cleaned up. We all good with that? Jennifer, you good? Yes? Okay. All right. Okay, so now we have to find our c such that f of c equals f sub ab, which really means it's the x value where this function happens to have 2 as its y value, right? So to do that, our function is 1 plus x squared. So to do that, you just have to set the function equal to your average value and solve for x. So take 3 seconds and solve for x. All right, you get plus or minus 1. However, the c is only 1. Why is the c only 1? Because I don't know if you remember this from the original mean value theorem, but your c has to be in what's called the open interval from -1 to 2. So you can't include an endpoint as a c value. So even if it works, deep down you'll know it works, but the only true answer, c, would be 1 on the open interval -1 to 2. All right. Good. Everyone understand how to find C? Just a little algebra. Yes, Emma.
You have to write your answer like just equals 1 on
Yep. You could actually just write C equals 1.
Okay.
Yeah, that's all you have to do. Yes, Keegan.
This seems kind of easy. How could we make this like 20 times better?
Funny you should ask, right? Okay, no, we're really not, it's not that much harder, but we're going to have it in a context of an application problem in just a second. But first, it's Benjo question. Eliminate part D. You don't have to do part D. Okay. Notice this is 2011 number 2, which means calculators are allowed, right? Okay. All right, I'm going to read this through, and then I'll start you on it. As a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for t in the interval 0 to 10, where t is measured in minutes and h of t is the temperature measured in degrees Celsius. Values of h of t at selected values of time t are shown in the table above. Use part A. Use the data in the table to approximate the rate at which the temperature of the tea is changing at t equals 3.5. Show the computations that lead to your answer. I think you all can do this. Derivative from a table, you can do it. Part B. Using correct units, explain the meaning of 1/10 times the integral from 0 to 10 of h of t dt in the context of this problem. Then use a trapezoidal sum with the 4 subintervals indicated by the table to estimate 1/10 times the integral from 0 to 10 of h of t dt. So, quick question. Are you just stretching? Okay. Does the trapezoidal sum approximate this entire expression? No. What does it actually approximate? Just the integral. So whatever you get, you're going to have to multiply by 1/10, right, to get the whole thing. Okay. And then finally, evaluate the integral from 0 to 10 of h prime. Using correct units, explain the meaning of the expression in the context of the problem. This is an FTC Part 2, straight up definite integral. You can do this. 3 parts, 10 minutes, whiteboard starts now. Recording right now? I am, okay. So, for part A, we're approximating a derivative at 3.5. 3.5 follows right here. So you would go up 1, down 1, do slope with a secant. So you get 52 minus 60 over 5 minus 2. And when you work that out, you get negative 8/3. Did it ask for units? No, then don't give them. So, good. You guys decided to give the exact and the rounded decimal?
Oh, yeah, we're special.
Okay, or you're just risking more than you need to, right?
Oh, yeah.
You got this? Just stop. Live on the edge. Okay, all right. Okay, good.
It's at the top.
Oh, I see it. Yep, good. Oh, good. You guys didn't even simplify. Like, you super were like, no, that's perfect. They get full credit, right? Beautiful. Well done. All right. So, everyone gets perfect score for part A. All right. Part B, using correct units, explain the meaning of 1/10 times the integral from 0 to 10 of h of t dt. Gosh, if only we'd learned something today that relates to this part. What does this look like? It looks like the average value. And it's the average value of whatever is here, right? So in this case, it's the average of whatever h of t represents, which is the temperature of the tea, right? So this is saying from 0 to 10 minutes, this represents the average temperature of the tea in degrees Celsius. So, okay, you guys, the average temp of the tea from 0 to 10, but you get a 0 because you don't have units for your output or units for your input, which is a shame, because your explanation is great. You're just missing units. Average temperature degrees Celsius from 0 to 10 minutes. You don't say of the tea, but I think they would still probably speak in. Okay. It's the average temp of degrees Celsius, 0 to 10. Okay, again, you don't say of the tea, it's what is the average temp of, but yeah, I think they take it. This is the average.
What? No, you continue. We erased the average. Yeah, we erased it.
Oh, and then so the average temperature. This is part of this line.
Part of that line.
Oh, okay, then it's perfect. Yeah, good job. All right. Okay. Average value of the temp in degrees Celsius of the function h of t. There, okay. Don't say two of those. Average temp in. Oh.
I just like drew an arrow because I wanted to fix value.
Okay, but then if you're saying average temperature of the function, don't say average temperature of the function h of t. Say average temperature of the t. Right? Yeah. Okay. On the interval 0 to 10. Minutes. Good. All right. Average temp in degrees Celsius from 0 to 10 minutes is good. No one's saying of the t. Ah! Da, 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 da. Okay, the average temp of the tea, beautiful, in degrees Celsius, okay, over an interval of 10 minutes.
Yes.
Okay, I would say I know this is being picky. Always just play safe and say from 0 to 10 minutes, right? Give them beginning and end. Or you can say over the indicated 10-minute interval. Otherwise, it just says an interval of 10 minutes, which doesn't necessarily mean that 10-minute interval, which is being really picky. They probably would take it anyway. So, but I'm just, I'm being picky. All right. Average temp of the tea from 0 to 10 minutes. So this is almost perfect. What's missing? Degrees Celsius. Yeah. Units, units, units. Units for output, units for input. Make sure you're putting your units for everything. All right. Part C. Oh, I didn't do the trapezoids. Oh, okay. Trapezoids. So 1/2 goes out front. Do these trapezoids have equal widths or unequal widths? Unequal widths. What's the width of the first trapezoid? 2, and then times the sum of the heights, plus 3 times sum of the heights, plus 4 times sum of the heights, plus 1 times the sum of the heights. So 2 plus 3 plus 4 plus 1. This right here looks perfect with a 1/2 for the trapezoids and the 1/10 because it's in front of the integral. Perfect. I don't know what the answer is. But it looks like several groups got 52.95, so I'm going with that. That's correct. Or 1,059 over 20? Okay. Okay. Yeah. So either one, they both look correct. Oh, okay. This one? Oh, yeah. Good. Okay, you did the trapezoid sum and then times by 1/10. That's totally fine. Yes. It does not. You do not have to put units. But you should know what they are because you just wrote it in your explanation. But I wouldn't attach units here because if for some crazy reason your units were wrong, then you'd still get your points for your numbers, right? But I don't think they would double ding you on bad units. They just take off one. All right. Last part. Integral from 0 to 10 of h prime. This is just a straightforward integral. So you do the antiderivative of h prime, which is h from 0 to 10. So this is just h of 10 minus h of 0. 43 minus 66. You get negative 23. Using correct units, explain what this means. Well, let's just think about it. It's the temperature at time 10 minus the temperature at time 0. So what is it? It's the net change in the temperature of the tea from 0 to 10 minutes, right? In degrees Celsius. So the net change in the temperature of the tea from 0 to 10 minutes in degrees Celsius, the net change in degrees Celsius of the tea. This is perfect. Well done. Yeah, good job. All right. 0 to 10 minutes. Okay. This would not give you credit. What's wrong with it? The word rate. Yeah. So guys, when you have an integral of a rate with nothing in front, it's the net change of the antiderivative. It's the net change of the amount, not the net change of what's there, right? Average value, it's the average of what's there. But for when you're not doing an average value, when you're just doing a plain old integral, it's the net change in the amount. That's why, and you kind of pick that up, right, when you actually do it. They're trying to help you, believe it or not. You don't think they are, but they really are. they're trying to help you by making you evaluate it first, because then that should kind of say, oh, well, this is just the change in temperature from 0 to 10, right? Okay. So anyway, so yeah, if the word rate is there, you lose the point. Okay, you should say net change of the temperature of the tea again, but yeah. Okay. Oh, you guys wrote A-Rock, which is yes.
I was wrong.
Okay. Alright. Net change in the temperature in degrees Celsius. Does that from 0 to 10 minutes apply both to parts B and parts C? Is that why it's in the middle here? Okay. Alright. Good. Good. No. Yeah, that's good. Overall, these are really good, right? A few little issues with not writing units on your explain, and there will be at least one explain problem on your test, so it's good to practice. Okay, that is it. I'm going to minimize this. Let's go back to this. We're not going to do 2010 today, but we might do it later.